Now you will go through the actual coding implementation of the interconnect. So I have written the whole module or the whole design in multiple files. So these are the files, and finally I have included all the files into a single file, which will be compiled as a design in the final system Verilog code. The first four files are of general in nature, and the next three files are the AXI to OCP conversion part, and the next two are the OCP to AXI conversion part, and this is the final DUT code. So the first one is the general definition.sv, which is containing the type def needed or used in the RTL and the TB code commonly. So I have added type def for the OCP response and the OCP command and the AXI write response, which are specific to the OCP and AXI signal protocols. Next is general macros .svh, which we have already discussed. So here I have defined macros for a flip-flop with asynchronous reset, flip-flop with enable and asynchronous reset, then a 2 input mux, 4 input mux, 8 input, and finally a 16 input mux I have defined here. So we can use these macros directly by using a tick the macro name in the final design code. So the next one is the interface.sv file, where I have defined all the 5 AXI interface and the OCP interface. So you can see that interface AXI write interface with an input clock and reset. Then I have listed all the AXI write interface write address channel signals, which are AWID, AWADDR, AW length, AW size, A burst, log, cache, port, and valid and ready. And so these 4 signals we are not using in our design. So we'll be using ID, address, and length, and the valid and ready. So this is as per the interface description, which we have already learned in last session. And again, in this interface I have added 2 mode ports, a master and a slave mode port, so that I can use this interface in a master system Verilog code with this mode port, and in the slave system Verilog code with the second mode port. So in the master mode port, the clock and reset are input, and all the signals, which is WID, length, size, everything is an output, and only the slave is driving the ready signal. And in the slave mode, all the signals are inputs and the ready is an output. And in the same way, you can see the interface definition for the AXI write data channel, which with the signals WID, W data, strobe, last, valid, and ready. So here we are not considering strobe, as our system is a simple design. Again, there are 2 mode ports for the master and slave with appropriate signal direction. And in the write response signal, there are again signals specific to the AXI write response channel description: BID, B response, valid, and ready. And in the read address interface, again you can see RID, address, length, size, burst, log, cache, port, valid, and ready signals, out of which we are using RID, address, and length signals, and the valid and ready signals. So again, there are 2 mode ports, which is master and slave. And in the read data interface, the RID is there, then the read return data and the read response, and finally the last and valid ready signals are there with 2 mode ports, slave and master. And this is the interface definition for the OCP channel. So you can see that M command, M address, all these are defined as per the OCP signal description, which again we had covered in the previous session. Again, there are 2 mode ports, a master and slave, to use the signals appropriately in a master and a slave client. The next file in the design is a FIFO.sv, which is writing a FIFO module with a parameterized depth and width. And this also you had learned in the previous session, how to write a FIFO. So this code is exactly same here. In the next session, you will be going through the implementation details of the actual AXI write front end module.